Hi, Assalamualaikum. My name is Muhammad Roslan. My matrix number CD240348. So basically, we are from group 11. So our topic that we select for the group assignment, which is group project. Our title is Steady State Heat Conduction in a One-Dimension Road. So basically, our code course is BDA 24402, which is differential equation. So our lecturer name is Prof. Madya Dr. Hamidun bin Saleh. So for a second slide, I will introduce our group members, our teams, which is my teams that contribute for the group project. So basically, just two of our teams that contribute for this group project. So first, me, my name is Muhammad Roslan. My matrix number CD240348. And second one is Muhammad Akmal Hamizan bin Muhammad Nazri, CD240364.
Assalamualaikum warahmatullahi wabarakatuh. Today I want to present about introduction for our project. First, functional differential equation are equations that involve functional derivative of a dependent variable with respect to more than one independent variable, commonly space and time. They are used to describe system where quantity vary continuously. In engineering, partial differential equation play a very important role because many real physical phenomena such as heat transfer, fluid flow, variations, and diffusion cannot be accurately described using ordinary differential equation alone. Heat conduction is chosen in this project because it is one of the most fundamental application of PDD, partial differential equation in engineering, and provide a clear and practical example of how mathematical models are used to solve the engineering problem. So the next slide, I will present about engineering problem description. First, the system study in this project is a solid road with uniform and homogeneous material properties along its entire length. Then one end of the road is maintenance at a higher temperature, while the opposite end is kept at a lower temperature, creating a temperature different than that drive heat flow. Next, heat transfer is assumed to occur only along the length of the roads, and any heat loss from the side of the road to the surrounding is neglected for simplicity. The last one, the problem is analysed under steady state condition, meaning the temperature distribution along the road remains constant with time. So this is our schematic diagram for our project.
So for next slides, I will present about the governing equation, which is there are three equation. So the first one is Fourier law, which is heat flow from a high temperature to the low temperature due to thermal gradient, which is the formula is Qx equals to negative K times dt over dx. So the second governing equation is Laplace equation, which is no heat generation. So basically, the formula we used is t squared t over dx square is equals to 0. So the last governing equation that we use in our group project is Poisson equation with heat. So this for the third one is with heat generation. The formula is d squared t over dx squared, which is equal to negative q over k. So for the next slide, I will explain about the mathematical formulation. So basically, the mathematical formulation explain how the physical heat conduction problem is expressed using partial differential equation, which is PDE. So basically, the formulation is based on the Fourier's law of heat conduction and the principle of energy conservation under steady state condition. So which is where temperature does not change with time. So when there is no internal heat generation inside the road, the governing equation reduced to the Laplace equation, which is presents steady state heat conduction without its without heat source. And so when uniform internal heat generation is present, so the governing equation becomes the Poisson equation to account for the additional heat produced within the material. So in the project, basically, in the project, temperature is assumed to vary mainly along the length of the root for analytical solution, while a two-dimension formulation is used for computational visualization. So constant temperature are specified at both end of the root as boundary condition, and assumptions such as steady state operation, constant thermal conductivity, and one-dimension heat flow are applied to simplify the analysis.
Okay, next slide about analytical solution. First, for the Laplace equation, where there is not internal heat generation, the temperature distribution along the rod is linear. This linear temperature profile indicates that the temperature gradient is constant between the hot end and the cool end of the rod. Next, for the Poisson equation, internal heat generation is present within the rod, which adds an additional source of energy to the system. So, as a result, the temperature distribution become parabolic and the maximum temperature occur at an integral point rather than at the boundaries. Okay, so the next slide about numerical data and assumption. This slide shows the numerical data used in our analysis. The rod length is 1 meter with the left end at 100 derajat Celsius and the right end at 20 derajat Celsius, which create heat flow along the rod. The thermal conductivity is assumed to be 200 watt per meter Kelvin, representing a typical metallic material. For the Poisson equation case, internal heat generation is included to represent heat producing component. This value allows us to study realistic steady state heat conduction.
So for the next slide, I will explain about the computational visualization. So basically, for the computational visualization, we are used Python. So Python was used to illustrate the steady state temperature dispute governed by the Laplace equation. Temperature is treated as a function of two special variable, which is t, x, y, where x represent the length of the root and y represent the transverse direction. So the contour plot show a linear temperature gradient along the x direction, while the temperature remains uniform along the y direction. So which is consistent with the analytical solution. This computational visualization enhance understanding of the partial differential equation PDE solution and satisfies the requirement of using computational tools involving multiple independent variables. So for the last part of my presentation is about result. So I will explain the result based on our group project. So basically for the case without internal heat generation governed by the Laplace equation, the temperature distribute along the root is given by Tx equals to 100 minus 80x. So the temperature decrease linearly from 100 degrees Celsius at the left end to the 20 degrees Celsius at the right end. So with a midpoint temperature of 60 degrees Celsius. So the linear variation indicates a constant temperature gradient along the route. So using Fourier law, the calculated heat flux is constant and equal to 16,000 watts per square meter. Confirming the steady state heat conduction. So for the case with internal heat generation, governed by the Poisson equation, the temperature distribute follow by Tx equals to 100 plus 170x minus 250x squared. So unlike the Laplace case, the temperature profile is parabolic and the maximum temperature occur inside the root and approximately x equals to 0.34 meters with a maximum value of about 128.9 degrees Celsius.
Okay, next about discussion. This slide shows the discussion for our result. First, the Lapsley equation represents an ideal heat conduction case where no heat is generated inside the material. Heat only flow due to the temperature difference at the boundaries. In contrast, the Poisson equation is more realistic because it includes internal heat generation. This situation commonly occur in electronic device and mechanical components. When internal heat is generated, the overall temperature increase and the temperature distribution change shape and just its magnitudes. And lastly is understanding the difference between Lapsley and Poisson equation is important because it helps engineer design surface and more efficiency thermal system and avoid overheating and material failure. Last slide about conclusion. This slide shows the conclusion for our project. First, this project successfully demonstrates how partial differential equation can be used to model steady-state heat conduction in a solid road. Next, by using both Lapsley and Poisson equation, we show that different physical conditions, especially the presence or absence of internal heat generation, significantly affect the temperature distribution. Then, using analytical and computational method, we were able to clearly understand the temperature behavior and heat flow in the system. Overall, this study highlights that partial differential equations are powerful and useful tools for solving real-world engineering heat transfer problems.